Our next talk, going from galaxies to exoplanets, our next talk will be by Casey Brinkman from the IFA Hawaii on a glimpse into studying rocky planets with fiber-fed spectroscopy. Take it away, Casey.
All right, can everybody see my screen okay?
Looks good.
All right. So hi, everyone. My name is Casey Brinkman. I'm a NSF GRFP at the Institute for Astronomy in Hawaii. And yeah, today I'm going to be talking about what we can learn about rocky planets with fiber-fed spectroscopy. So for my thesis, I'm attempting to answer two fundamental questions in exoplanet science. One, how diverse are the compositions of Earth-sized planets across our galaxy? And two, how are these compositions related to the abundances of their host stars? So to do this, I measure the densities and model the interior compositions for a sample of rocky exoplanets. And today I want to tell you about a very special one, TOI 561b. So TOI 561 is a star in the galactic thick disk that's known to host at least 3 transiting exoplanets, including a super-Earth. Now, this is a very unique super-Earth for a number of reasons. One, it's one of the oldest Earth-sized planets that we know of in our galaxy, over 10 billion years old. It's one of the only Earth-sized and therefore presumably rocky planets beyond the thin disk of our galaxy. And it's one of the only ultra-short period planets that's been discovered in the galactic thick disk. On top of this, as the thick disk stars often are, TOI 561 is iron depleted and alpha enhanced. And in fact, it's one of the most metal poor exoplanet host stars that we know of. All of this paints TOI 561 as an ideal system to explore the compositions of planets formed in unique conditions, very different from our own solar system. So, to first order, we can assume that Earth-sized planets are primarily made of a rocky mantle and an iron core. Despite the fact that liquid water and an atmosphere are what make the Earth habitable to life, they actually compose an insignificant fraction of the planet's mass. When we study hot super-Earths that orbit even closer to their host star, this further decreases the likelihood of significant water or atmospheric contributions to the composition. So in order to determine a planet's composition, we first need to measure its density. So we do this by measuring the radius from the transit of the planet in front of its host star, in this case with TESS, and we measure its mass from radial velocities, or hereafter referred to as RVs, and this will be the focus of my talk. So this planet does have 2 previously published mass values. The Weiss et al. Team measured a mass of 3.2 Earth masses using the high-res spectrograph on Keck, while Lacedelli et al. Measured a mass of 1.6 Earth masses using the Harps North spectrograph. These 2 discrepant mass values produce wildly different densities and suggest entirely different compositions. While the high-res value suggests the planet is rocky, the Harps measurement suggests that this planet has an extensive volatile or water envelope. To resolve this tension, we want to use a third spectrograph, Maroon X, to measure the mass of this planet. So we conducted simultaneous observations using both instruments with the hopes of measuring the mass of a planet with a fractional uncertainty of less than 10%. So why use these 2 spectrographs in particular? High-res, as I'm sure many of you here know, is one of the most reliable spectrographs and has been pioneering exoplanet science since the 90s. But it is limited to RV precision of roughly 2 meters per second. Maroon X, on the other hand, is a newly commissioned spectrograph that is capable of producing RVs with sub-meter per second precision. In part, it's able to do this because it is a fiber-fed spectrograph. This eliminates the need for an iodine cell, allowing higher SNR with less exposure time. And this, in addition, it's able to produce a more stable PSF. Together, Maroon X will be able to increase the precision of the measurement of our mass value, while high-res will help to provide an RV baseline with which we can help validate the Maroon X measurements. Another fiber-fed spectrograph that's slated for use soon is the Keck Planet Finder that we've been hearing a little bit about. So it has a similar design and specs to Maroon X, and what we see from Maroon X should give us a glimpse into what KPF might be capable of achieving. And what we see from Maroon X is incredibly promising. So here we've shown just one of our 3 runs of Maroon X in February of this year. Using just these values, we can measure a mass of 2.7 plus or minus 48 Earth masses for the planet. This is a 17% fractional uncertainty with just 16 RVs, as opposed to a 35% uncertainty with 80 measurements from high-res. However, the high-res measurements that we took were able to validate these Maroon X measurements. We can see strong agreement between these two spectrographs. And while the intrinsic uncertainties on the RVs plotted for each data set are comparable, there's much less scatter amongst the Maroon X RVs as shown with the RMS. So these results are incredibly promising of what KPF will be able to do. So combining all of our data now, 70 Maroon X, 80 high-res, and 80 HARPS measurements, we get a mass of 2.3 plus or minus 0.17 Earth masses for the planet. This is a fractional uncertainty of just 7%. And in fact, this is the most precise RV mass measurement that we have for a super Earth-sized planet with a radius less than 1.5 Earth radii. And this mass translates to a density of 4.3 grams per cubic centimeter. So we can now compare TOI 561b to the broader population of exoplanets. Here we've shown all exoplanets with radii between 1 and 4 Earth radii that have RV mass measurements. We've also shown the solar system planets. Oh no. Anyway, here's the Weiss-Marcy relation for average planet density, and this helps show the distinction between rocky super-Earths and gaseous sub-Neptunes. And here are the density curves for a planet with an Earth-like composition, a composition of solid rock, and a composition of solid iron. And here is where TOI 561b falls. Not only is this a low density planet, as one would kind of expect given its host star abundances, it's in fact the lowest density super-Earth that we've discovered to date. So, what does this low density tell us about the planet's composition? We used the open source software Burnman, which was originally developed by geodynamicists to model the interior seismic activity of the Earth in order to explore the interior possible compositions of the planet. So we use it to build planets with different ratios of rock, iron, and ice at a particular radius, and it solves equation of state for each of these materials at interior temperatures and pressures, and then it returns a mass for the planet. So we can use this to see what compositions produce mass values that are consistent with what we measure. These results are best summarized as a ternary diagram. Each point on this represents a planet that we built using Burnman, and that planet is composed of a fraction of iron, ice, and silicate rock. The color of the point indicates the mass of the resulting planet. And so here we can see all of the compositions that produce a planet within 3 standard deviations of our measured mass value. We can see that there are no compositions that contain just iron and silicate along this 0% ice axis. This means that there are no solutions for a planet that agree with our mass measurement within 3 standard deviations that are composed of just iron and rock. Because this planet orbits its star twice a day and is incredibly hot with an equilibrium temperature of around 2,500 Kelvin, it is not likely to host large fractions of water or ice, especially on the order of 20 to 30% of the planet's mass. So therefore, this planet does need a gaseous envelope in order to have the mass and radius that we measure. So because it has an atmosphere, we can't determine the exact ratio of iron to rock in the solid portion of the planet. But we can use the limits to put a limit on the extent of the atmosphere that composes the planet's radius. So on the minimum core side, we can have a core that's made of entirely iron at 1 Earth radius. Or if the core is made entirely of rock, it would make up 1.4 Earth radii. This means that the atmosphere of the planet has to compose somewhere between 3 and 30% of the planet's radius. So how can a planet that is so small and so hot have such a significant atmosphere? So volatiles that are trapped in the interior of the mantle during planet formation can be outgassed through volcanic processes, replenishing an atmosphere slowly over time. Additionally, the planet could be irradiated so intensely by its host star that the rocky mantle itself is evaporating. We do, however, know that hydrogen and helium would likely photoevaporate on timescales much shorter than this planet's lifetime and shorter than the timescale in which it can be replenished through outgassing. We're still investigating which other species of heavier volatiles might be able to maintain an atmosphere over its 10 billion year lifespan. So these results are going to be coming soon. So in conclusion, we obtained simultaneous RVs of TOI 561 using both Keck High-Res and Maroon X. With our new and previously published RVs, we were able to measure the most precise super-Earth mass to date, and this gives us just a small glimpse into what the KPF will be capable of. This density of TOI 561b is the lowest super-Earth density measured to date and will require an envelope made of heavy volatiles, unlike most sub-Neptune-sized envelopes that we see. And lastly, this helps show us that the diversity of Earth-sized planets across the galaxy is much greater than we could have previously imagined. So that's all, and I'll take questions now. Thanks.
Thank you, Casey. We have plenty of time for questions, so maybe we'll start online. Let's see, there's a question from Carrie. Great talk. Are there other planets you wish to do similar studies with?
So this planet is fairly unique. The only planet that is at all similar to TOI 561b is 55 Cancri E, I believe. And that is one of the planets that I'm looking at observing in the upcoming year because it has a much larger, a slightly larger radius, placing it slightly over the 1.5 Earth radii boundary between super Earths and sub-Neptunes, but it also is believed to have an envelope of some sort because it's too low density to be rocky. So I am looking at other planets that could have this composition.
A little question. Is that okay? Yeah.
Yeah, absolutely. Go for it. But the audio is a bit weak, so maybe try to get closer to the mic.
Hello, hi, Chris. So, are there any prospects for doing transit spectroscopy for this subject? If the atmosphere is that large, transit signal really significant.
So I wasn't really able to make that out. Could someone repeat it maybe?
So what is the prospect for doing transit spectroscopy on this subject if the atmosphere is that large?
I'm sorry, I'm still having a hard time hearing.
I think the question, if you can hear me better, the question is, what are the prospects of doing transmission spectroscopy? So actually probing the atmosphere or understand the atmosphere using.
Yeah, so that's actually something that I've been bouncing around with both my advisor, Dan, and Lauren. So we're thinking of applying for HST observations of this in order to at least see if there's to see if we can get a phase curve for the planet and see if the night side temperature is the same as the day side temperature, or if the night side temperature is warm at all. I think my suspicion is that the planet is still too small to do actual atmospheric spectroscopy. I haven't done any, looked too hard into it because I don't know a lot about atmospheric spectroscopy. So if there are people in the room who know more about that, please talk to me about it after, but I have a hunch it's still a little too small.
I hope I translated the question correctly, Dimitri.
That was right. Yeah, I'm sorry, Lauren. Can you hear me?
A little bit.
Okay, a little bit. I'll just talk really loud. Okay.
Okay, any more? I think there maybe one more from the audience, if there's any. I don't see anything else online.
There's nothing local. Oh, there is something local. We're bringing it.
Hello, I'm not a finance person, so this question might be really naive. So, if a fraction of the planet is made of volatiles, what fraction would it be, and is that significant compared to other planets?
It was very difficult to hear again, at least for me. I don't know.
Yeah, me too. Sorry.
Hello, can you hear me now?
A little bit.
Okay, so I'm gonna try repeating it. So if the fraction, if a fraction of the planet's mass is made of volatiles, what fraction do you think would it be, and how does it compare to other planets that have been studied?
So that's going to depend heavily on what the species of the atmosphere is. So for hydrogen and helium, which is the only calculation that I've done so far, it had to have been like less than a 0.01% of the planet's mass. So enormously smaller. Obviously, if it's a heavier volatile, it's going to be more, but I don't think, in general, even for sub-Neptunes, it's not more than 10% of the planet's mass. So I think we're looking at the order of up to like a single percent.
Okay, I think we're out of time, so let's thank Casey.